Welcome everyone to our exploration of matter, the very fabric of our universe. Today, we'll delve into the microscopic world to understand how particles come together to form everything around us. In this session, we'll delve into the microscopic world, where atoms and molecules dance in a delicate balance, forming the vast tapestry of materials that make up our universe. We'll discover how these particles combine to create compounds with unique properties, how mixtures retain the characteristics of their individual components, and how we can represent and understand these processes through chemical equations and observable physical changes. Join us as we embark on a journey to unravel the mysteries of matter and witness the transformative power of chemical reactions. Pause this video and copy the information to your notes. Everything around us is made up of matter. Matter is anything that has mass and occupies space. But matter can be found in a variety of forms and compositions. Let's break it down. Matter can be divided into two main categories: pure substances and mixtures. Pure substances have definite chemical composition. This means they are made up of only one type of particle. Pure substances can either be elements or compounds. Elements are the simplest substances. Think of gold, oxygen, or copper. They can be broken down further. Compounds like water or baking soda are made up of two or more elements chemically bonded. Mixtures are made up of two or more substances, physically combined, not chemically. That's the difference. So you can see different components in a mixture. There are two types: homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures look uniform, like salt dissolved in water, or even the air we breathe. Heterogeneous mixture have different components that are easily visible, like a bowl of cereal or a sandy beach. This diagram helps us organize the different ways matter can exist, whether elements, compounds, or mixed up. Matter is the building block of our world. Imagine walking into a room where everyone looks the same, thinks the same, and even wears the same outfit. Sounds a bit boring, right? But in the world of chemistry, this uniformity is what makes pure substances incredibly special and valuable. A pure substance is a bit like that room. It has a definite and constant composition. Whether you're looking at a drop of water or a piece of diamond, every single part of pure substance is exactly the same as the whole. Now let's shrink down to the size of atoms and take a closer look. From a particle perspective, all particles in the pure substance are identical twins. They look the same and they stay the same, regardless of where you find them in the substance. This uniformity gives pure substances their unique properties and makes them predictable, which is something scientists love. What does this mean for us? It means that when we work with pure substances, we're dealing with materials that offer certainty. Their boiling points, melting points, and reactivity remain unchanged. This predictability is crucial, whether we're conducting experiments, manufacturing products, or exploring the natural world. As we move forward, remember the simplicity of pure substances opens up a world of complexity and possibility. They are the building blocks of matter, and understanding them is a key to unlocking the mysteries of both the natural and the engineered worlds. Let's pause here for a moment. Can you think of other substances or other examples of pure substances that you might encounter in your daily life. The world around us is made up of tiny building blocks called atoms that combine in different ways to form everything we see. Let's dive into the fundamental components of matter: elements, molecules, and compounds. Imagine if you could write the story of everything in the universe, from the air we breathe to the stars far beyond our reach. What letters would you use? In the language of chemistry, these letters are known as elements, the basic building blocks of all matter. Each element is a unique type of atom, and what makes each type unique is the number of protons it has. Like the letters of the alphabet, elements combine in countless ways to form the words, sentences, and stories of the material world. But here's what sets elements apart: they are the simplest forms of matter that still retain their identity. Elements cannot be broken down into simpler substances by chemical means. This is what makes an element, whether it's gold with its 79 protons, giving its luster and weight, oxygen with 8 protons, essential for life as we know it, or helium with 2 protons, making it the second lightest element and perfect for floating balloons. So, as we explore the universe from the smallest atom to the vastness of galaxies, remember, it all starts with elements. These fundamental entities from gold, oxygen, or helium are the Legos of the universe, building everything we see, touch, and experience. Each element carries its own story, its own properties, and its own role in the tapestry of existence. Now, think about this. If you could be an element, which one would you be and why? Discuss how these fundamental pieces of matter mirror the diversity and complexity of the world around us. Picture a dance where atoms, the smallest units of matter, come together to form partnerships, groups, and communities. This dance of atoms create what we know as molecules. A molecule is formed when two or more atoms are chemically joined together, bound by forces that tie them into a lasting embrace. These atoms can be the same, dancing in unison, or different, bringing a variety of moves to the floor. Consider the air we breathe, rich with oxygen molecules, each consisting of two oxygen atoms linked arm in arm. Then there's water, the elixir of life, where two hydrogen atoms and one oxygen atom can come together to quench our thirst and nurture the world. And let's not forget carbon dioxide, a molecule made from one carbon atom and two oxygen atoms, playing critical role in our planet's climate and the cycle of life through photosynthesis. Molecules like oxygen, water, and carbon dioxide are the building blocks of the environment and life itself. They tell the story of our atmosphere, the waters of our planet, and the air that fills our lungs. These tiny dancers, invisible to the naked eye, choreograph the rhythms of life, from the simple breath we take to the complex ecosystems that sustain us. Now, imagine if you could create your own molecule, what atoms would you choose to join in this intricate dance of life? How would your molecule contribute to the world around us? This time, picture a chef in a gourmet kitchen, combining ingredients in precise amounts to create delicious dishes. Similarly, compounds are formed when two or more different elements chemically joined together following the nature's recipe to the letter. But here's the twist. These elements combine in a fixed ratio, a strict recipe that cannot be altered without changing the compound itself. For example, table salt is always made of sodium and chlorine in a 1-to-1 ratio. This precision ensures that every single molecule of a compound, like the table salt, baking soda, and methane, has the same composition and properties, no matter where you find it in the universe. Think about it. Every time you season your food with table salt, or when you see water forming on a cold glass, you're witnessing the incredible result of elements combining together to form compounds. These aren't just mixtures, they are new substances with properties distinct from the elements they are made from. Methane, a simple compound, CH4, is a gas that can fuel our homes and rockets into space. So, why does this matter? Because understanding compounds give us insight into everything from the air we breathe to the medicines that heal us. Now, let's brainstorm. What are some everyday compounds you encounter and what elements are they made from? Pause the video and copy this to your notes. As we journey through the microscopic world of chemistry, we've uncovered the nature of pure substances. Let's crystallize our understanding with a key insight. All compounds are molecules, but not all molecules are compounds. This distinction is crucial in the realm of chemistry, where the specifics matter as much as the broader concepts. Molecules are like social gatherings of atoms. They can be a simple get together of the same kind of atoms, like O2, where two oxygen atoms join hands. Or they can be a more diverse assembly, like H2O, where hydrogen and oxygen come together. Compounds, on the other hand, are always a diverse gathering. They arise when two or more different elements chemically bond, creating something entirely new. And here lies the magic of chemistry. When elements are chemically joined to form compounds, they transcend their individual identities. The atoms no longer exhibit their solo properties, but collaborate to showcase entirely different characteristics. It's as if by joining forces, they unlock new superpowers, distinct from the element they originated from. This transformative power of chemical bonding is what builds the diverse material world around us, from the water that quenches our thirst to the air that fuels the fire of life. Compounds and their molecular architecture play the leading role. So, remember, the strength of chemistry lies not just in the atoms, but in the bonds that bring them together, creating a universe of possibilities. As we wrap up, think about this. How do the compounds around us influence our daily lives? And what might be the implications of altering these fundamental building blocks? Pause the video and copy this to your notes. Picture a masterpiece of art where each brush stroke and color remains distinct, yet together. They create a scene bursting with life and complexity. This is the essence of a mixture in the world of chemistry. Unlike compounds, where elements chemically bond to form a unified whole, a mixture are like gathering of individuals, each maintaining their unique identity while contributing to a collective ensemble. A mixture is a combination of two or more pure substances. This can be elements, compounds, or both. They don't chemically bond. Again, they don't chemically bond. This means each substance in a mixture retains its individual properties. Imagine mixing sand and iron filings. They coexist, but remain fundamentally unchanged, each retaining its inherent characteristics. The beauty of mixtures lies in their versatility and reversibility. Since there are no chemical bonds tying the substances together, they can be separated using physical means. For instance, our earlier mixture of sand and iron can be separated with a magnet, pulling away the iron filings and leaving the sand behind. This separation is a testament to the individuality of each substance within a mixture. So, why is this important? Understanding mixtures and their properties allow us to explore and manipulate the material around in nuanced ways. It's the principle behind everything from the air we breathe, a mixture of gases, to the foods we eat, which are often complex mixtures of compounds and elements. Now, let us ponder a moment. Can you think of a mixture you encountered today? How might you separate it into its pure substances? Just as our world comprises a vast array of landscapes, from the uniformity of desert sands to the varied terrain of mountain range, mixtures come in two different types: homogeneous and heterogeneous. Let's dive into what sets them apart and why it matters. On one side, we have homogeneous mixture, the masters of disguise. These mixtures are so well mixed that their composition is the same throughout. They're uniform, consistent, and you wouldn't be able to identify the different substances in them just by looking. Think of a solution of sugar in water or a cup of perfectly blended coffee. Every sip tastes the same. Contrast that with heterogeneous mixtures, the variety packs of the chemical world. These mixtures flaunt their diversity, containing visible different substances or phases. A bowl of cereal with milk, a rocky beach, or even the Earth's atmosphere are all examples. Each part of a heterogeneous mixture might give you a different taste, texture, or appearance, celebrating their non uniform composition. But why does this distinction matter? In science, as in life, understanding the nature of mixtures helps us predict their behavior, utilize them effectively, and even separate them back into their pure components when needed. Whether it's extracting drinking water from a mixture of understanding how pollutants separate in the air, the knowledge of homogeneous and heterogeneous mixtures is the key. Before we move on, take a moment to think. Can you identify an example of each type of mixture in your surroundings? How might the difference between homogeneous and heterogeneous mixtures affect the way we use or separate them? Let's review. Pause your video and answer the questions. The correct statement about sodium oxide is letter C. Sodium oxide, or Na2O, is a chemical compound, not a mixture. Compounds have fixed composition by mass, meaning that they are made up of their constituent elements in specific ratios. In this case of sodium oxide, it always consists of two sodium atoms for every one oxygen atom, and this ratio does not change. Let's break down why other statements are false. Letter A, it is a homogeneous mixture. This is not true because sodium oxide is not a mixture at all. It's a chemical compound with a definite formula and structure. For letter B, it melts over a range of temperature. So, pure substances include compounds like sodium oxide have a specific melting point at which they change from solid to liquid, not a range of temperatures. It can be, letter D, it can be separated into sodium and oxygen by physical means. So sodium oxide is a compound, and compounds cannot be separated by physical means. Sodium oxide is a compound, so chemical reactions are necessary to break down compounds into their elemental components. For the second problem, the statement that suggested the substance cannot be an element is letter A. This is because elements are pure substances that consist of only one type of atom and cannot be broken down into simpler substances by chemical reactions, including electrolysis. Electrolysis is a process that involves passing an electric current through a substance to cause a chemical change. This chemical change usually results in the decomposition of a substance into different substances, elements, or compounds. If electrolysis of a substance produces two different products, this indicates that the original substance was composed of more than one type of atom. Hence, it is not an element but a compound. Take, for example, water. If water undergoes electrolysis, which is water is a compound, it will produce H2, which is gas, and O2, which is another gas. Let's examine why the other choices do not suggest that the substance cannot be an element. For letter B, it reacted and dissolved in water to give a colorless solution and gas. Elements can react with other substances and still be elements. For example, metallic elements often react with acids to produce hydrogen gas and a salt in solution. The result of an element with water doesn't necessarily mean it's an element. Rather, it shows how it reacts with another compound, water in this case. For letter C, it has fixed melting and boiling point under standard conditions. This characteristic is typical of pure substances which can either be elements or compounds. Fixed melting and boiling points are indicative of a pure substance because they have a consistent structure and composition. Therefore, the fact that a substance has fixed melting and boiling points does not rule out the possibility of it being an element. For letter D, when heated in oxygen, it can form two oxides. Two oxides. So, elements can combine with oxygen to form oxides, and it's possible for one element to form different oxides under varying conditions or in different stoichiometric ratios. For example, carbon can form both carbon monoxide or CO and carbon dioxide or CO2, which are two different oxides of the same element. Carbon combined with oxygen, it can form CO or carbon plus oxygen, if it is a complete combustion, will form CO2. So production of carbon monoxide is for incomplete combustion, while production of CO2 is a complete combustion. So both are reacting with oxygen. So this does not indicate that the original substance wasn't an element, just that it can form more than one type of oxide. Let's have two other problems. Please pause your video and answer the questions. To determine which diagram represents a mixture of only compounds, we need to look for a diagram that shows different groups of atoms bonded together, with no single or uncombined atoms present. For diagram A, shows chains of alternating black and white balls, which represents atoms, and two black balls bonded to a white ball. Since there are no single balls and each group contains more than one kind of atom, this diagram represents a mixture of compounds. So A is the answer. Let's look at the others why they are wrong. For B, it displays groups of two white balls, two black balls, as well as three white balls as different elements. Since we're considering the black and white balls as different elements, rather, the presence of groups with only white balls indicate that this diagram also contains an element, not just compounds. For diagram C, it shows groups of two black balls with one white ball and groups of two white balls bonded together. This diagram includes both compounds, two blacks and one white, and an element, two whites together. So it is not a mixture of only compounds. Diagram D depicts groups of two black balls bonded together and groups of two white balls bonded together. This suggests that there are both compounds. Rather, this suggests that they are both elements and individual elements, so it's not just a mixture of compounds. It is a mixture of elements. Thank you for listening. Please proceed to the next video.